So thank you for this opportunity to present this work. For those of you who were here in the morning, I said that the main interest of my research group is in Bayesian inference on these very high dimension discrete spaces. And I have a number of students working with this. I presented in the morning one such work, like cover classification. This work is on a general problem called community detection, which is very common in social networks. I'm working with a student on this, Legion Fun. Legion couldn't come, so I'm presenting for her. And I'll do a shameless plug and advertisement for another very good talk tomorrow in the morning to Ian Johnson, which is also working a similar problem. So let's get going. So the goal of this problem, this is a very familiar problem that has been around since the 70s at least. So the idea is that suppose you observe n multivariate normal observations with some dimension p, and the idea is that you want to estimate the mean, but most importantly the concentration matrix or the covariance. The concentration is just the inverse of the covariance. So you want to do that. So here's an example where I have a number of samples, let's say 25 samples, and here you have 50 components of this multivariate vector. And you can see that in some samples, some components go together, right? So they should be correlated, strongly correlated. If I decide to plot the concentration matrix, my estimate of the concentration matrix, or the true concentration matrix that generated this data, you realize that there is some pattern. There are some blocks of components that have high concentration. And the idea behind using the concentration is that each entry in this concentration matrix measures the partial correlation between the two components. That is, if we correct for all the other components, and we measure the correlation between any two components here, then we have this property that if the partial correlation is 0, then we shouldn't observe any specific correlation between them. So we want to correct for the other variables as well. We just don't want the correlation, but we want the partial correlation. That is, we want to correct for the other components. And this is a very common problem, as I said. It's been around at least since the 70s. Was defined by Dempster in 72, this idea of covariance selection. And the main block here, the main hurdle that we have to overcome is that the fact that P is usually large compared to N. That is, the dimension of this matrix that you want to estimate is usually much larger than the number of observations that you have. So you want to estimate P plus 1 choose 2 entries in this matrix, potential entries, but you only have n observations. So what should you do? If you just try to do the naive covariance, sample covariance estimate, you know that that's going to be singular, right? It's going to be rank deficient because you're only using any variable. So the rank of the matrix is at most n, but you want to estimate a larger variance. So this is not possible. So one solution here is to look at this concentration matrix and say, look, if I know that my P is much larger than n, I have to assume something. And the assumption that you have is that some components are conditionally independent of others, given all the other members but those two. So suppose if I take number 43 and component number 11, I can say, given all the other components, I assume that 11 and 43 are conditionally dependent, which would mean that I'll have a 0 entry here in this matrix. So one way of solving this problem is to assume that this concentration matrix is sparse. And that's why we call this covariance selection. You want to actually not only estimate the entries of this matrix, but you want to also select which entries won't be 0. And that's the idea. In our case, there are other twists. One twist is that some of these components can be what we call popular. That is, you might have very high partial correlation to the other components. For instance, if you focus on number 8 here, you can see that it has a lot of partial correlation with a lot of other components. So 8 is a popular component in this case. So you want to take that into account. The other twist here is that the components, and this is more visible, the components can somehow cluster, so the concentration matrix is expected to be roughly block diagonal. In this case, you can clearly see that you have pretty much 3 blocks. You have this block here, you have in 2 bigger blocks, this one and this one, right? And it's pretty much sparse other than that. So you want to take that into account. So how do you do it? So there are many previous approaches. I won't list the literature here, but as I said, this is an old problem. It's been around since the 70s, and there are many ways in which you can do this. The most common ones is just look at this as a variable selection problem and put your L1 regularization or L2 regularization, that is, you do ridge regression or loss solve and so on. So I won't talk about these. These type of approaches can solve the problem reasonably well, but they won't take into account those 2 points here, that some components might be popular and that the components can cluster. So we won't also choose that. So how do we do? First, let me talk about this very nice characterization that we have about the concentration matrix. If I have my NIID multivariate normal with this mean and this concentration matrix, then we can associate to each one of the components of this matrix here a related graph, such that I don't have an edge between 2 components. Each component is a node. I don't have an edge if those 2 are conditionally independent. Or, since this is a normal distribution, conditional independence means that you have 0 partial correlation. So if you see a 0 here in this matrix, it means that there is no edge. It's if and only if. If I have any other entry that is different than 0, then I have an edge. So for instance, associated to this specific concentration matrix, I have this graph here. So those components here in the beginning correspond to this red cluster here. These components on this big block here correspond to the green, and these components here and this block here correspond to the blue nodes. Okay, so that's how we do this correspondence. And why is that useful? Well, that's useful because you can see that if you want to induce regularization on C on the concentration matrix, that means that you want to induce sparsity and that associated graph. And how do you do sparsity in this case? How do you induce sparsity? We take a look at this graph and look at it as a latent graph, and then besides this likelihood here, right, this is how I generate the data, I can put a prior distribution conditional on the latent graph. So A is the adjacency matrix of this graph, that is 1 if there's an edge, it's 0 otherwise. And so I can say that the ijth entry of the concentration matrix, given that I have or doesn't have an edge, has this distribution here. We call this the spike and slab prior. It's a very well-known model that we can use to do variable selection. If the edge is there, I sample from a normal with a very long tail, so very high variance. If I don't have an edge, then I sample from a spike, that is a normal with a very small variance. Or you can even use, if you want strong shrinkage, you can even use a direct delta at 0 if you want. So, okay, we're going to use this. This is pretty much equivalent to any kind of L1, L2 regularization. So what's the gain in having this specific representation? The gain is that now we can set another hierarchical level on this model, and we can actually capture what we want. That is, we want to have the popularity, we want to characterize the popularity and the fact that the components can cluster. And to do that, we put another level, and to model what we call a community behavior. That is, we want to use what we call a degree-corrected stochastic block model. You don't need to know what that is, but it is the following. I just put a logistic regression on aij's. That is, suppose that I have these coefficients here, then the probability of observing an edge is given by this inverse logit here of this linear combination. So let me break this down. If I observe the labels, sigma are the labels. They tell, for instance, whenever you see the red cluster, the sigmas for all the nodes in the red cluster is 1, let's say. The sigmas for the blue cluster is 2, and the sigmas for the green cluster is 3. If you have 2 nodes that belong to the same cluster, then I can boost the probability of observing an edge there. What we want to see is this kind of community behavior. You want to see clusters like this case here, right, where you have a lot of edges. This specific cluster of community is very dense in edges. You see a lot of edges between them, but we don't want to see many edges across clusters. So it makes sense to have a gamma between any 2 same groups to be high to boost the probability of observing an edge between them. And then we also correct for the fact that some nodes or some components might be more popular than others by fitting specific intercepts for each one of the nodes. So that's how we correct for the popularity. So we have terms to correct for the popularity and a term which is more important that captures this community behavior. To guarantee that you have this community behavior, then you set some constraints. Actually, we have to set the gamma between any 2 components to be 0 for identifiability of this model, but then to guarantee that the probability of having an edge across groups is smaller than the probability of having, in the logit scale, of a probability of having an edge within a group is smaller, we either priorly set the gamma between any 2 different communities to be negative. That is, in a larger scale, we have a lower probability. So there's another level. I mean, I'm overlooking a lot of the priors here. We also set priors on the gammas and the etas and so on. And we set some labels that the probability of observing some sigma, some specific labels independent come from a multi-node distribution. I just have some specific probability of belonging to community 1, 2, 3, 4, and so on. For now, we can assume that we know the number of groups, the number of communities. But eventually, in the application that I will show you, what happens is that we fit this model for many different sizes of groups, and then we choose the best one based on BIC or any other type of model selection criteria. I'll talk briefly about posterior inference. Posterior inference in this case can be a little bit challenging. We tried both approaches. We tried to just find the map estimate of each one of these parameters, and we also try an MCMC approach. And I'll just briefly mention that if you want to find the map estimate, then we can use a few tricks. And the most important tricks that we use, you can check the paper on the proceedings to check the details. But we use the sweep operator, which is very versatile and helpful in this case because it will give us basically the Schur component of the covariance matrix that we can use to update the probabilities. And we also use Cholesky up and down dates to make things faster. Every time we want to include some specific edge, we just have to update the covariance. We never recompute the covariance from scratch. We only update the covariance. If you want to use MCMC, it's a lot slower, not surprisingly. And we have, but in this case, the gain that we have is that we have a better estimator, which is a permutation invariant central estimator, which unfortunately I won't have time to talk about. But the idea is that you have to be careful if you don't use the map. If you want to use another estimator that takes care to account the component-wise differences, it's a specific loss function, you realize that, well, wait a second, it doesn't matter if the red cluster is labeled as 1 and the blue cluster is labeled as 2. You can swap the clusters and you still have the same assignment. So we have to take that into account, and that's why we call this permutation invariant. So let me briefly show you two examples, two simulation studies. So one is this simulation study here. We took some benchmark networks from this very famous social network benchmark set. It's based on a physics model by Lantichinetti, Fortunato, and Adicchi. And they sampled, they give you some specific latent graph. Based on this latent graph, I sampled the C and all the other parameters and then sample the data, and then I try to reconstruct the latent network and the concentration metrics and so on. And here I'm comparing lasso estimates for different penalties with our method knowing the latent network and not knowing the latent network, and with just a random sample. And basically we do better, we fare much better, and there's not much of a difference if you know the network or if you don't. We have very good, so this is the log of the norm, the L2 norm between the difference between the estimated and the true one to the norm of the true one. And we fare much, much better than the lasso and Eleanor equalization in general. This is the runtime, this is the price we pay. I mean, it's a little bit slower than lasso. Lasso is faster, so there's no free lunch, right? I mean, if you do better, it's because we spend more time exploring the model. And the main source of errors are due to false negatives. That is, it's very hard, especially if you have a small sample size, to predict that an edge is there when it actually is. So it's much easier to just not find the edge. If you crank up the sample size, then you start seeing more edges, but then there's a cost to pay, which is now increasing a higher false positive rate. That is, we put edges where it shouldn't be. There's a nice case study. We have basically summarized this. We have observations from expression arrays from different bacterial communities in dental fields. So there's dentistry goes to take samples from the healthy people and people with periodontitis in different sites in the mouth, and they observe some specific bacterial communities. And we know that bacteria work in communities, that is, they have this very nice symbiotic relationships that they unfortunately can cause disease. And the idea is that we want to identify which communities are the interesting ones. What happens? What is the differential effect between communities from healthy people to actually people with periodontitis? So we have this data from expression arrays between healthy and patients with periodontitis. We fit a mean model where we have a simple effect and we have a bacterial effect. There is some missing data. We use some EM along the procedure. We plug in an EM in the procedure. I won't talk about that. And then we identified the number of communities, in this case is BIC, Bayesian Information Criteria. This is the inferred network. We inferred that there are 3 communities in this case. So this is the inferred community, latent community for the healthy patients. You can see that it's very sparse. There's basically not much going on in this case. And this is the inferred latent network for the patients with periodontitis, with the disease. And you can see that it's much more connected in this case. And this is a plot of alpha centrality for those 2 networks. That is a measure of centrality in this network, but when you use the actual effects from the mean model, that is, you want to see not only what changes here, what bacteria are now more important in center in the symbiotic relationships, but also you want to measure the change in the effects that they have from the healthy to the disease. And we notice that most bacteria that are known to be very pathological, they have an increased alpha centrality when you compare the disease to the healthy ones. So this is a very good result. Just to following back with our collaborators on this. So to summarize, the idea here is that we have a hierarchical model for regularization and community behavior. That is, we wanted to do covariance selection, but there are a few twists. We want to capture this fact that the components cluster, that we might have some components that have different degrees of popularity. It's a potentially large parameter space, so we need to be careful with and try to derive a potentially efficient estimation procedure. So we do have a map estimation procedure, but we also have an MCMC version of it. And the idea is that we want to have more representative models. So you cannot just plug in your sample covariance estimate. It won't work in this case. If you just want to use lasso, L1, L2 regularization, it will work, but it's not as well as this. And we want to extend this formulation to account for weighted graphs. You can use other generalized linear models and move this to other applications. And I'd like to thank NSF for the support and my collaborators, Carvalho and Atibaia, for the